Uh, is my screen visible? Yeah, thank you. So we'll just quickly walk through the implementation part of Nebase that we had pending yesterday. So we'll just quickly walk through 15 minutes now. Followed this, we'll have a decision tree, and post the break, we'll start with SVM, feature engineering, and finally go with hyperparameter optimization. So even in this, we'll partly cover hyperparameter optimization. We'll just see the implementation of grid search and random search. So this is the agenda for today. So as we've seen yesterday, the name base, we've seen the basics, and we've seen all this part, and we were there in vectorization part of. So basically for this implementation, we are considering the fetch 20 new news groups data from sklearn, and these are the different categories of data, the text data that's present inside the 20 news groups. So among this data, we are considering four different columns of data, four different categories, four different classes, namely religion, Christian, space, and graphics. So these are the four different categories of data that we'll be investigating, or we'll be taking for a naive-based classification. So once that is done, we are just having a look at how the data internally is present. So which goes with generally for a news article, what are the basic things we see? We see from subject, originator, organization, distribution, and so on. So and followed with it has the core content, it has the core news information that's present with regard to the federal hearing. So once that is done, so yesterday we had seen about the differentiation. Generally, to convert a textual information into a vectorized form, there were two initially count vectorizer was used, so which basically gets the count of the repetition of words. So it gives us a tabular column where we find how many times the number of words is repeated. But there were some problems with this because it put too much weight on words that were appearing very frequently. Let's consider the auxiliary verbs or the conjunction words like and, that, is, was. So these are words that we use repeatedly in our textual information, but rather they do not have much potential information present in our that has to be taken for our classification. So in order to overcome this, we've seen how TF-ID vectorizer works. So TF-ID vectorizer basically weights the word counts by a measure of how often they appear in the documents. Excuse me. So we use the TF-ID vectorizer from sklearn, and we just call it and give the fit.transform to convert our given textual information into a weighted form which is done by the TF-ID vectorizer function or the algorithm itself. So once we've got this TF-ID vectorizer, so this is the one that will be directly giving to our system or model for training. So here we are using multinomial naive Bayes because we have multiple classes. We're having 4 plus classes. So we go with multinomial naive Bayes. Initially, we had split the train data and the target data, which we're directly giving, and we are loading the model. So once that is done, as we all know, model.fit does the training part. So after model.fit is completed, our next task is to do the prediction part. So once the prediction part is done, we've got the predicted labels, and after getting the predicted labels, as we all know, the next part is to compare the predicted labels with that of our original data. So for this, we are using a confusion matrix. So upon the visualization of confusion matrix, we find that this particular class, the 187 value, that is between the religion Christian, the textual content between religion Christian and that of the general religion talk, that is there's a misclassification occurring. So this shows that where our system basically is having a issue, and the kind of work that we'll have to put into. So this is a basic implementation of how text classification works in our using the naive Bayes. And similarly after that, we just send few test samples, and like payload to ISS, it classifies as space, and similarly Islam versus atheism, it classifies as Christian, and resolution it tells to be graphics. So just a quick summarization, like where and when to use naive Bayes. So these are or like the pros and cons. These are like extremely fast for training. It's very straightforward. There's a probabilistic prediction, and it's very easily interpretable, like as we have seen yesterday. The next goes with sentiment analysis using Twitter tweets data. So as we have seen yesterday, we were actually, as we have just looked in, we have seen we're just taking out a Twitter tweet data. I'm just opening the CSV file for us to have a look. Since the data is actually quite huge, so it takes some time. Just a minute. So before this could load, there are like few things that I just want to share. Like, yeah, I think it's loaded. Just a quick check. Is my screen pointing to a CSV file? No participants. Like, I've actually opened the CSV file. Is that screen getting shared? Okay, cool. Okay, just a minute. I'll just share this. Yeah. Is it pointing to a CSV file now, which reads ID, user, and text? Yes. So this is the data. Yeah. So this is the training data that we have that we are going to use for sentiment analysis using Navies. So this is actually a Twitter tweet data where we have tweets of different people there, and using this data we are now going to see how we are going to do the sentiment analysis. So how this data stands different from the previous one was, in the previous one the textual content was in the form of a paragraph, and inside the paragraph we do not have lot of other special characters for us to do the pre-processing task, because when we're getting the train data itself directly, the as we've seen, the information was in the tabular form, and the to and from was directly removed from the to and from part was directly removed, and we were as such processing with that of the original text content. So we did not do much of pre-processing. So in order to expose to even a better level of pre-processing in the text in the textual data as such, we are now considering this particular example where we're having a lot of special characters. Say, as we know, Twitter tweets, we often tag the people with an @ sign, right? So we'll just have a quick look about how we are going to remove these kind of special characters inside the data, and how we are again going to give it into the algorithm for training. So this is what we are going to see today. Just a quick check. Now I should have a screen pointing to sentiment analysis using multinomial naive-Bayes with cross-validation and grid search. Is it visible? Yes. So I'm not actually running the code now because the data set is quite huge, and it might take a lot of time to upload the data and start running it. You all can just run and check it. I'll be handling a session tomorrow morning. So in case you guys, in case there are any further clarifications required, we'll just walk through it tomorrow. So as we all know, we are just importing the regular things as such. We're calling the data, and we are importing it as a pandas frame. Follow that as the regular checks we do. We are seeing what is the count of the information that is present by, and we're just grouping by and seeing what is the kind of target we're having. These are like the basic steps that I hope you've seen in the previous classes. And following this, So our first task is like these are Twitter tweets, right? Basically, what we type in our social media platform. So there are a lot of possibilities that we use apostrophe words like current, can't, and couldn't, and those kind of apostrophe words. So in such cases, when we're having a real-time data from such environment, our first task is to remove the apostrophe words. So for that, what we do, we just identify the potential apostrophe words that is present in English grammar, and we are now replacing them with that of a regular the full form of the word without the apostrophe. So like shouldn't, which as goes as should not, and she's as goes as she is, because the algorithm is not designed to learn an apostrophe with a s. All the algorithms that we are doing, like we are basically going to give this to a TF-ID vectorizer, correct? So TF-ID vectorizer is going to process it with the word as such. Now TF-ID vectorizer is not familiar with the apostrophe s, so that's the reason we convert from the apostrophe s to that of the is form of the verb. So once that is done, we are just initially giving a dictionary that's going to tell us like where we are actually where we are actually changing this. So once this dictionary is done, we are defining a def function called preprocessed text, which is going to do all our pre-processing. So the first thing goes with, we are just removing the HTTPS part of it, as we all know. The second thing is like we often tag people when we are when we put a tweet or when we put any kind of thing in social media platform, and we all know this @ symbol is used for tagging. So our next task is to remove the tagging part of it. Next, so here we are actually planning to do a sentiment analysis. So our concern over here is the predicate or the real matter present in it rather than the subject. So we are not concerned about to whom the subject is actually pointing to, but rather we are concerned about the predicate part of the content. Like for example, let's say John is good. Okay, we are not concerned about at with John, the noun part of it. We're not concerned about whom it is pointing to, but we're rather concerned about is good, the part that is after it, the content that is after it. So our task is to remove the @ symbol along with the noun present after it. So we don't want the name of the person whom it is actually tagging, but rather we are concerned about what he's telling about the person. So that's the reason we are removing the @ symbol too. And further we are making all the alphabets into the lowercase, and we are replacing the apostrophe words. The dictionary that was called on top, we are just calling it to make all the apostrophe words into the full form. And followed this, we are just removing the punctuation marks with these set of pre-processed text. For this we use the import library in Python, the import array in Python. So following this, as we can see, so this is our original input data as we saw, nocturnally anyway, and now Abby and I share. So this the person whom it was tagged is not important for us, so we're just removing that. And following with, we see our content is now in the full form. And similarly here, like all the apostrophe words are replaced with the full form, and all the punctuation marks like here with the comma after mountains are removed. So this is the basic pre-processing that we do to convert our real-time data into the form that can be given to TF-ID vectorizer, followed with the multinomial naive Bayes. So here what we're doing, we are comparing we are comparing the multinomial naive Bayes performance with that of a lexicon based method. As we know, sentiment analysis can be done with numerous methods. So one among them is a lexicon based method. So for the lexicon based method, there's a library called Valdo. So Valdo sentiment, and we are just importing the library, and we are giving the data into it, and we are seeing the performance of the library. We get an accuracy score of 66%. Following this, here comes the area of interest, which is a multinomial naive Bayes. Here, as we seen, the TF-ID vectorizer is better than the count vectorizer. So we're giving it to a TF-ID vectorizer, getting the data in the vectorized form. Following this, we give to the train test split, and we call the multinomial naive Bayes with alpha. So alpha is like a smoothing parameter that we've already seen. Following this, we are going into the training the model with model.fit, that is np.fit, and we go with prediction. So finally, as we know, we use these three common metrics like precision, recall, f-score, and support to evaluate our data. So generally, the accuracy score is used when the data set is balanced. When we have an imbalanced data set, we go for precision, recall, and f-score. So as we all know, so support is actually telling us how many positive samples, the two true samples we are getting from the given data. So and we see the confusion matrix like this. So this one, what we did was with the original data set. So in order to see how our performance is varying after the pre-processing, so we've seen some major pre-processing steps that has to be deployed with when we're doing with the real-time data. So in order to visualize or interpret how much performance upgrade is happening after we apply this text data, or after we apply this particular pre-processing steps. So to visualize that, what we are doing, initially we give the original data itself to TFID, and we see the performance. So we get around say 76% of accuracy score. Now what we do, now we apply the same naive Bayes with the pre-processed text data to see how much is the accuracy improved. So we see from 76, it's like we're having a minor, it's actually, since it is a randomly initialized one, we get a minor variation. When we rerun it again, it might vary. I mean, we might have a improved one. So as we see, there's a like a minor variation every time we run, right? Especially this happens with the neural network and all. Depending upon in what distribution our initial weights are initialized, or like depending upon how our initial values for weight is initialized, is only the convergence happens. So more specifically with respect to neural network or other machine learning algorithms that have initial coefficient values that have to be initialized, the initial parameter plays a very important role in convergence, because we don't know how the parameters are going to change. When the parameters are initialized in a manner that it might help the convergence, then the algorithm trains faster. So it is not practically possible for us to always know how the weight has to be initialized. Specifically, when we tomorrow we'll be seeing CNN architecture. So in that place, a weight initialization plays a very important role. The weight initialization itself will decide the kind of accuracy that the algorithm can give. So the weight initialization plays such an important role, almost like that of the learning rate. So in all the cases, it's not practically feasible for us to always give the correct weight initialization. So because of this, what happens, our final accuracy score might vary slightly. So we have a like a plus or minus tolerance value. So we cannot correctly tell when the weight initialization varies how the performance might vary. So in such cases, what we do, and also regarding the hyperparameters. So as we all know, every algorithm has its own hyperparameter, right? So in naive Bayes, we don't find much of hyperparameter there. Only in multinomial we have one particular parameter, that's the alpha one. After this, we'll be seeing a decision tree, and we'll be seeing SVM, so which has a very crucial hyperparameters whose performance, or like whose value is very very important for our accuracy. Like they are the key value for us. So once we vary that, like the performance might increase or decrease so much. Say for SVM we have the kernel, like for decision tree we have its own hyperparameter, and so on. So in such cases, selecting the optimal hyperparameter is important task for us in order to get the model generalizing very well on our unseen samples. So when I give unseen samples, our ultimate target is the model has to perform well on the unseen samples and generalize well. So in that case, selecting the optimal hyperparameter is like exploiting how far my model can perform well. Even though we have designed a very good machine learning algorithm, if you are not going to set a best hyperparameter, the model's performance will drastically vary or drastically drop. So for setting the best hyperparameter, there are many techniques. So one of the fundamental technique is the grid search and random search, so which most of us are familiar with. So what happens with random search? We just randomly pick the hyperparameter. So basically hyperparameters are like interlinked. So for example, if we take a convolutional CNN architecture that we'll be seeing tomorrow, always the learning rate will be interlinked with the activation function, and the activation function will be interlinked with the weight initialization. So it's not that rather I investigate only one single hyperparameter, but most of the time it happens to be a chain or interconnection that's often existing between a hyperparameter. So in such case, what we do in random search, we see a relationship between like how the performance varies when I have two hyperparameters. So in random search, we randomly select the two hyperparameter and we investigate the performance of the model. Whereas in grid search, we ensure that all the possible values of hyperparameter are tested. So therefore in grid search what happens, there is no possibility that we will miss any hyperparameter, but in random search there is a possibility that we might miss any hyperparameter. So on an initial case, like as a beginner, this is the first time we are taking an algorithm, and the first time we are putting a test data, in such case random search is good. But like when we are on a serious note, after the initially understanding how which algorithm works and which model is best, so because initially we'll do some trial and error method, right? So after the trial and error method, we ultimately go for narrowing down our algorithm and our hyperparameter and finally setting it before we take the final result. So in such case, grid search is better. So this is how we go. So post this, we have other techniques also, like the Bayesian technique, and we also have certain libraries in Keras, that's a deep learning framework. So we'll see that when we are seeing our CNN session tomorrow, because we have not exposed you to Keras, right? So tomorrow we'll just have a brief introduction about the deep learning framework called Keras. So post that, we'll see how there are few libraries itself in Python that help us for this hyperparameter tuning. So post our CNN session tomorrow, we'll just have a small brief about how those libraries will help us tune the hyperparameter optimally. So today we'll see how grid search and random search is done using the sklearn library, which we are already familiar with. So before we initialize grid search or random search, as we saw, the first step is to identify what are all the hyperparameters. So for our task today, that goes with sentiment analysis of Twitter tweets, what are a possible hyperparameter? That is the count vectorizer, because we are now converting a text data into a vector form. Then goes with the TF-ID. Then the TF-ID transformer is like another one function that we're doing, and finally it goes with multinomial linear base. So this is the pipeline of functions that we'll be using. And what are the parameters that we look, and we go with n-gram. So yesterday itself we saw about the n-gram by gram. So then it goes with n-gram by gram, and whether I have to use my TF-ID or IDF. So this again goes with the true or false, and the which normalization, L1 or L2, and finally goes with the smoothing parameter that's there for the multinomial layers. So while we have to use the grid search, a first step is to tell the model, tell my grid search algorithm that what are the parameters I'm going to initialize. So that's the first one what we do. So after telling the parameters, we also have to give the range, like within what value it has to be present. For example, n-gram, the possible combinations that we tell the model to search for, because we have to tell the model to search, we have to give the A, B, C and X, Y, Z, right? So we have to tell within what range the model has to look out for the hyperparameter. So that is given in the form of this particular list. So TF-ID, the possible values are true or false, and norm it goes with L1 and L2, and CLF, the alpha value goes with this one. So always our tuned parameters should be the one that's always used in a pipeline. Say in the other case, if we are going for the other algorithms, other possible things might be like uh, learning rate or epoch value, or let's say the decay value for L1 and L2. When we're using a regression and all, we have to specify the value of alpha, right? So that's a key hyperparameter. So in those cases, the value of L1 and L2 might be our other possible parameters to be tuned. So once we give that, as we all know, we have to split the train and test. So follow this, we go with the grid search. So this is how we call the grid search. So it is called as grid search cross validation. So I hope participants are already exposed to the cross validation in the second session, in the day 2. So I'm not spending much time on this. Suppose this, we just call it, and we'll be giving what are the different functions that the model has to look for, and what are the different tuned parameters it has to do. And the next one goes with the cross validation, how many times it has to run. So since you're already exposed to it, I'm not spending much time. Suppose that we see what is the classification report we are obtaining, the accuracy score with the confusion matrix. So this is the kind of results we obtain along with the confusion matrix, and the best score is found to be, and the best score is found to be 0.78 out of all the possible combinations in grid search. The best score was obtained with 0.78, and the best parameters was 0.1 for the smoothing parameter, and L1 norm with false, and n-gram value is 1 to 2. And when we are implementing this grid search, this value of CV is also very important. That is the split that we are giving in cross validation. So usually it is like a thumb rule, when because this cross validation, right? In cross validation, we are splitting the data into different parts, and the model runs for all the fold of it. And collect, I mean, like selecting the best value of fold. So whether I'm going to have 5-fold or 10-fold is also a hyperparameter, and the number of fold will also influence the performance of the model. So usually, like a thumb rule, depending upon the size of your data set, it's always advised to go with 5. First, we'll have to check for 5 split, that is cross validation to be 5-fold cross validation. Then we go with the 10-fold cross validation. It's like a thumb rule. We usually check with 5 and 10. Post that, we have to look for other combinations. But as a beginner, we initially exploit with the 5 and 10 values, right? So that was about the sentiment analysis. Now going in for PCA. So it was like a quick walkthrough that we did yesterday. I'm just quickly walking through. So looking in for the PCA part, so as we all know, what PCA is doing, it's doing the dimensionality reduction. So initially, for this for basic level of understanding, what we do, we plotted some data on a scatter plot of 200 dimensions. So after that, we are calling PCA. So it's as simple as that. As we all know, it's just a 3-line code. We import it from sklearn, and post that we specify the number of components. So what is the how much dimension it has to be reduced? That's n is equal to 2. And following that, we see how the model is behaving after it is getting fit. So fit is basically doing the PCA for us and getting the dimension to be reduced. So this is the basic, these are important PCA components, and this is the explained variance we get. And after that, we see we actually plotting that important 2 components, the PCA components, onto the real data, and we are saying what are the 2 important vectors, because we're reducing from 200 to 2. So as we see, we can actually find 2 arrow marks here, and the line with the highest one shows that's the most important principal component, and it has the higher magnitude than the other one. So this is a basic level of how PCA works for a scattered data. So generally, so our ultimate target here is, when I'm having a higher dimensional data, I'll have to find out the dimension, or I have to find out the direction that has the highest importance when compared to the other. In a similar way, we'll just see how PCA behaves for different kind of data. So this is actually about the data that has MDS linkages. So post PCA, it's actually reduced to 100 dimension, and we see how well the dimension has been reduced. And similarly, this is for a hand return digits. So after dimensionality reduction, basically it's for a image data. For dimensionality reduction, we find it's even performing better. And similarly, this is with the covariance of diagonal, spherical, and covariance of full type. And this was the random initialization. So finally, how clustering happens. And so these are the principal components. These are input data, and this is the principal component of our interest. And similarly, it goes with another image-based data. So this is about how basically PCA is used for dimensionality reduction. Now we'll look in for this again example where we have a 200 original shape to be transformed to 200 cross 1. Now going in for the one of the like important applications. So let's consider how PCA is applied for a hand return digits. So for that, we load the data set that's present inside sklearn. We load it, and we see the data shape. It's actually 1797, 64. These are like 8 cross 8 images. So basically, we have 64 pixels of information. That's 64 data points, and 1797 samples are present inside it. So our target here is to reduce from 8 cross 8, that is the 64 data points. From 64, our target is to reduce to 2 data points. So even after this 2, we are seeing how the model is still able to represent the original form. So that's our target here. Now when we apply the PCA2 as given generally, and we do the fit transform, and we see it projected on the sample, and we'll see a figure down below. So these are like just basics for us to refresh, so that it's self-explanatory. And choosing the number of components, always we see the number of components as relative with that of the variance. So we see how the variance is actually varying with that of the number of components, and our target is always to select an optimal value with respect to this.
Sandhya?
Yes, sir.
Just go down.
Yeah.
Sir plot. You just show the sir plot. Yeah.
This is the kind of relationship that we see. So from a 64 dimension
So
pixel
go to the
values.
surplot that no, I want to add one more point in that surplot. That is what I am asking. No, not this one. The last one. You're showing a one. So participant, I want to add one more point in this particular plot actually. What this plot says actually, this is we called it as a surplot. So this surplot explain how much variance, that means how fairly we are attains the variance with your minimum number of components, right? Look at this particular plot. It shows here totally we are having a 140 components, right? So what is our idea? We are trying to reduce our features, right? It is a 64 element, so it has a 8 rows. So it has a 8 rows because 8 cross 8 is a 64. It has a 8 rows. We try to reduce it as a 2, right? So what happened here? So instead of so this plot shows if it is a 0, the variance is very less. If you are slightly raising the number of component, the first 20 components, it captures the 75% of the variance in the particular data. Okay, so 40 components, we attain almost 85% of the variance, because this variance is much important while we are doing any classification application, because this variance to information only information for any kind of application. The further you want to investigate, you need a high variance to data that carries a more informations, right? So look at here, in the 100th component, in the 100th principal component itself, it almost reached the 95%. So further it is not required. So up to 100 it's more than enough for your application, because it takes almost all the variance information. Okay, so this is how we are identifying, or we are capturing the number of principal component by using this surplot, right? This surplot investigate how much PCA component which is used to extract the almost maximum variance of the data. Fine, thank you. New Sandhya, you just continue.
So using this, we see how 8 cross 8 pixel value is actually reduced to a 2 cross 2 pixel one. And after this, we'll look for another application of PCA that's used for noise filtering. So PCA can also be used for noise filtering in any kind of data. So for this, what we do, we already seen the plot. We've already seen the digits example in the previous case. We're taking the same digits and we're adding some noise into it, so we can see that the given image samples are added with few more random noise. Suppose that we are applying it to a PCA with that indicates that we are having a noisy data. And so that is the inbuilt sklearn function in PCA will accept a keyword called noisy. So with this, we'll tell that we are training the PCA on a noisy data, right? So when we're doing this, when we give the PCA dot transform, and when we are actually fitting onto the model, so we see that the PCA is able to remove our noisy components from that of a given data. So there's another application of what PCA can be done. And similarly, it goes with eigen faces, where we are able to select the feature selector for a given facial recognition application for PCA using PCA, right? So this goes with we are calling the icon face with that's present inbuilt inside sklearn. So it's called the fetch L FW people dataset, that's labeled faces in wild dataset, is made available through SO. The image, these are our image shape. So from that, we are calling the decomposition using the randomized PCA with the components to be 150. So from 1348 cross 62 cross 47, we are reducing the components to be 150. And once after that, when we see the data post PCA, we see that we are able to extract the most efficient features from the given phase data set, and we are able to reduce the dimension to a better level and remove the redundant data. So this is the other application of PCA on a image based task, and similarly it goes with the previous plot that we had discussed. So this about that was the features that we saw, and this is the original reconstruction. So this is the 150 dimension reconstruction of the original image. So this shows that PCA, so this is a full input dimension, this is a full image, and after reconstruction with reducing the dimension to just 150, we see that we're able to recollect, I mean PCA has the capability to extract the most important features and reduce the dimension for most of the important applications. So this finally goes with an other analysis summary. And this is one of the scratch implementation of Naive from scratch. So here we are having all our small, I mean, as we know, Naive has the probability calculation followed with followed the implementation of the exact Bayes theorem. So for that, what we do, we are taking the PIMA diabetes data set. So it is a data set that has diabetes count. So I'll just open it, just a minute. Just a quick check. I should have a value now. The screen should now be showing a Excel sheet with value 6, 148, 72, 35. Is it visible? Participants, I should, yeah, yeah. So this is the PIMA's data set that has a collection of different categories, like different information, whether the given person who is affected with diabetes is having we have a history of his data, like whether the person was pregnant or whether he was a male and female, what was his gender, what was his age, and so on. So each of the column represents one particular data, and getting all this data, we give it to a naive-Bayes classifier to classify our new test case, our unseen sample, or whether the given person can have a diabetes or not. So it's basically a yes or no type of classification. So for that, so and this particular application we are completely implementing from scratch. So initially we are reading the data set and we are splitting the data set, as we all know, and depending on the training size, and then we are separating it by label. That is the final value, whether the given person is having diabetes or not, the final yes or no value. And these goes with the implementation of the different processes, that is a calculation of mean, calculation of standard deviation, summarization of data, summarization by label, calculation of the probability. And this is the exact place where our equation is actually implemented from scratch in NumPy. Followed with that, we have the calculation probability, and then finally going with predict and getting the predictions out of it and getting the accuracy. So this is about how it's implemented at a basic level. So we'll just share this code to help you understand how it works in a in a binomial classification example. So, and finally, I'd like to conclude with few points about Naive-Bayes. So Naive-Bayes can be opted with respect to other algorithms. I mean, like when to opt for Naive-Bayes, basically. We have a lot of machine learning algorithms for classification. We have SVM, we have neural networks, and so on. So when will I go for Naive-Bayes? So we go for Naive-Bayes when the data is more mutually independent. So when we don't have much of interrelationship between data, so that is one of the place we actually go for the Naive-Bayes one, right? So, but rather the other algorithms, specifically with respect to SVM, and so we'll see that when we're having the session, we'll see when to use SVM, when to use Naive-Bayes, and when to use SVM and when to use logistic regression, and so on. So with respect to Naive-Bayes, we opt for Naive-Bayes rather than SVM or other places when we know that a given data is more of a mutually independent one, and because this works with completely a probability based one, right? So this mutually exclusive data helps us to work well, and in the next session we'll see what kind of data is best for SVM and so on. Okay, so any queries? and I'll be sharing all these files, so you should be getting it by today. And I've also sent the files with regard to matplot that goes with the basics of data science. So matplot was remaining, and I've shared it yesterday, so you should be getting it by today. And this set of naive based files, we'll be sharing it today. So any queries, participants? So shall we just proceed with the next session? I mean, with the next topic. Any queries? Yeah. Uh, so I think you can take on.
Yeah, fine. Participants, my screen is visible. Good morning to all. My screen is visible.
Yes, it's visible, sir.
Yeah. Yeah, I hope so. We are actually go through how to implement the naive-based classifier from the scratch. So we have discussed the so many applications where we are used the naive-based classifiers, and then finally, it's a classification. Always, obviously, we get the evaluation metric also. So at last, we are calculated the accuracy, precision, and recall, and the F1 score and support value. That is actually the one of the quality or evaluation metric for the classifiers, right? In the first session itself, I hope so. In the case of cross validation session itself, they may handled why we are moving into the different evaluation metrics apart from the accuracy, why we are measured the precision, why we need to measure a recall. I hope so. Just I try to say I try to add a one more point, why we are shifting considering the medical application. Okay, so your model is actually not properly working, but in the medical application what happens, data set is actually a huge issue, right? Even if we are in the COVID-19 data set also, it has actually the 2000 or 3000 data set for non-COVID, but for a COVID the data set is only 200. Okay, so just see how actually biased data set. Fine. So far during this time, what happened if your model is not properly working? Okay, but we don't know whether it is working or not. After we are evaluating the quantifiable value only, we can say it will work. Okay, so what happened during that time, your model is ready to give a uh, the false result. That means try to identify every patient is a non-COVID patient. Okay, so obviously you are having 100 data in non-COVID and you are having a 20 data in the class of COVID. So what happen if you calculate accuracy? You get a 80% accuracy, right? You get a 90% accuracy because we are concerned, especially for the medical image, what is actually the true value. If the class is actually comes under a COVID, it classifies as a COVID, that is also comes under your true value. If it is a non-COVID, you're classified as a non-COVID also, it comes under a true value, right? So what happened during this time, it shows all the data is actually non-COVID. So obviously you get the accuracy is 80%, but your model is exactly your model is not actually working, right? So for that case alone, we are that for this is the reason why we are shifting. Apart from the accuracy, we are moving for the precision, and we are moving for the recall, and we are moving for the other metrics, F1 score and all. Fine. I hope so you understand why I am insisting that, because we need to know, once if you are developed the model, the next step is we need to evaluate the quality metric. Then only we can understand how the model is actually working, right? Based on that only we have to improve the model, right? So this is the reason why we are moving for the other metrics, right? So yes. So today we are going to discuss about the decision tree. So yesterday I hope so we are covered the all the mathematical intuitions, all the mathematical concepts behind your dimensionality reduction and naive-Bayes classifiers, and how this naive-Bayes classifier is actually utilized for the text classification and your um, the spam and the non-spam classifications, right? All the in this particular application, all the concepts is similar, guys. It's if you understand the text classification only, you have to keep pick the right features, right words from the data, and you have to build the model, right? That is your idea, right? So that is how the naive basis works, right? Why I am picking the base model, because we are having so many dimensionality reduction technique. Why I am picking a PCA? PCA is base for all. Once if we understand the PCA exactly, we can easily build the advanced models, right? So here I am going to take a decision tree. So in the decision tree also we have so many different types of algorithm. We will see one by one what exactly the decision tree, what about, what is the operation of the decision tree, we will see. So generally, a decision tree is a graphical representation of all possible solution to a decision based on certain conditions. We are fixing the certain conditions. We are fixing the certain conditions. Based on that, it going to classify your data, right? So simply look at this particular picture. Here I am showing a tree. What is the structure of tree? The structure of tree is it starts from the root and it grows up, and then finally it gives a, it has a so many branches, right? Yeah, this is a structure of normal tree. Look at the particular picture here. That is actually the representation of your decision tree, right? So it also has a root node. So salary at least, that is your root node. So after the root node we are also grown the so many branches, so it looks like a tree like structure. That's why it is a tree. Then what is the purpose of building this particular tree? This tree is built because this tree is going to give, or it is going to take some decisions, right? It's going to make some decision based on your data. That's why we are named it as a decision tree, right? So okay, so just in this in this diagram I try to come up with some simple application, right? So here I try to build this decision tree, whether should I accept a new job offer or not, right? This is a scenario. Okay, as a person, whether I am going to accept a the offer or not, right? So first criteria. So what is the general criteria where you are also going for an interview? What is your expectation? You are expecting a salary, right? That is a potential need. Okay, that's why this salary is plays a root node. So a node which is a capable of having a potential variance, or a, we can say a potential uh, way to form the more branches. That's why that particular feature is going to fix as a root node, right? So in this scenario your salary is plays a root node. So what happened, I'm going to set the question whether my salary is at least 50,000. If it is no, I decline an offer. Okay, if it is a yes, next I am going to fix another criteria. What is my another criteria? Compute more than 1 hour. If it is a yes, I just decline an offer, or otherwise I am going for the further investigation. My further investigation whether they are offering a free coffee or not. If it is a no, I just decline the offer, or otherwise I accept the offer. This is how the decision tree is built. So in the decision tree, what we have to do, what we have to understand actually, how fairly we are fixing the questions, how fairly we are taking the proper attribute and fixing the questions, and from that question we are trying to take some decisions, right? This is how the old picture or old concepts about the decision tree. I hope so. You people are understand the basic definitions of a decision tree, and we will see what is actually what are all the terminologies which is presented and what are all the components which is presented in the decision tree. The components like root node, decision node, and leaf node, and all we will see in the upcoming slides. So for better understanding, we just simply go with the one small example how the decision tree is working. Okay, so look at this particular data set. So one thing, not only a decision tree, any problem while we are approaching in the machine learning or a deep learning, we have to investigate data set. You have to spend some time with your data set. Then only you can bring a model with the better accuracy, right? Okay, so what is the scenario about this particular data set? So this data set is here I am going to classify my fruits, right? Whether it is a mango, a grape, or lemon. So this is a three classes it's available, right? The one more thing I try to add the point here, the multi-class and multi-label. So this is actually multi-class. This is the example for multi-class because we are having a more than one class, right? That's why we says it is a multi-class, right? So label I will tell you later. Right here, let us consider the two feature is we are used here. One is a color feature and another one is a diameter. Okay, based on the diameter and the color, I am going to classify the leaf is mango leaf or grape leaf or lemon leaf, right? So what is the criteria here? The green color, it's a 3 diameter, it is mango. Red color, 1 diameter, it is grape. Obviously, okay, fine. So we understood that green and red is actually the root attribute which is used to classify the data exactly. But the another problem here it's existing, where the problem is actually uh, evolved. You just see here the second example, yellow 3, right? The yellow 3 is also a mango, yellow 3 is also a lemon. So 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 which one is we have to choose? We don't know, right? So we will see how this kind of problems are generally how the decision tree is approaching this problem. Okay, for our better understanding about the decision tree. So first what happened? So first initially I am going to build a cart algorithm, right? I will explain what are all the different types of algorithms are there in the decision tree and what is the major difference between the all those things, right? So first we are accepting the data sets. Okay, so the root node accepts the data set. So we have to understand which attribute is going to act as a root node, whether color is going to act as a root node or size is going to act as a root node. Okay, so initially I just set my diameter is going to act as a root node. Okay, that means the size is going to act as a root node. So this is my root node. Whether the data it comes inside in the root node, I am checking the rules is diameter is greater than 3. If the diameter is greater than 3, the decision is, that means the condition is true, it comes here. If condition is false, it comes here. If it is a false, you looks the false leg. Here it's a unmixed data. There is a no mixing up here, right? So you can't drill it up again and again from this particular leg. Am I right? Because already we don't have any variance data, so we can't drill this particular false leg, right? But look at here, we are having a mix up data. So here we are having a variance, right? So we have to uh, drill this particular data again. Then we have to come up with the unmixed data. That is our target, right? We have to come up with the unmixed data. That is our decision. So here we are come up with the decision grape only, right? So look at here. So one metric is we are going to, so we have to understand the the question fixing is important and attribute selection is much important, right? So when to so after we are fixing the questions and the uh, conditions, we have to know when to we have to split the that means where to we have to fix the nodes and where to we have to stop. That is the first condition. Second one is which condition is we have to build. Am I right? This is a two condition we have to concentrate while we are developing a decision tree. So the for the first condition where we have to build. So this for this condition, it's actually by using the Gini impurities. So Gini impurities is actually watching whether the variance is present or not. What about the impurity of the data? So look at here, here the Gini impurity is 0 because it's a pure data. There is a no impurity is present here, right? But look at here, some impurity is present. So here you have to again split. Compared to this, you have to start the your investigation, or you are going to fix the rules here. Okay, this is the first condition. The second one, what you have to do, you have to investigate the potential question, whether this question is able to classify your, are able to take a proper decision or not, right? That is what we have to understood so far. To investigate about the question, that means you investigate about the conditions. So investigate about the feature, we can say this is actually the features, right? So investigate about the features, we are going to use another metric, it's called as information gain. Okay, based on the information gain, how you are gained the information from that particular feature, that is actually the understanding of this metric, guys. So here, yeah, in this particular question, we understood that 35% of information is we are attained from the diameter of the data, and here the 11% of information is we are attained from the color of the data. Okay, so look at here what happened. So after we are checking the diameter, it comes here. Once it is true, we understood that once again it has a unmixed data, sorry, mixed data. So what you have to do, once again set the conditions. What is our condition? By using the rest of the feature is this one. So I'm going to fix is the color is equal to yellow. If it is a no, that means if it is a true, we are splitted as a, we are splitted here. If it is a false, it's we are splitted here. So we can understood this particular part is we can't split further, because you look at here, both the metric is equal. Okay, under this situation, decision tree not takes any it's failed to take a decision. It gives either one of these things. Okay, either a mango or a lemon, right? So this is how the decision tree is building. So you have to know which attribute is we have to use to split, and which question, that means based on your features, how to fix the conditions. Okay, so for this two statement, the quantifiable measures are your Gini impurities and information gain. So this is how the final classifications. So once it accepts the data, if it is a false, it exactly classified 100% grape. If it is a true, it is not it in this condition, it not takes any decisions because it has the mix up data. So it try to split once again. So this particular node accepts all the variance to data, right? Once again it try to split. So until you get the unmix up data, you have to drill again and again. Okay, this is how this particular decision tree grows. So in this application, we are fixed the two questions, right? So how we are fixed these two questions? We are not randomly fixed the questions. This question is we are investigated the data set, then only we are fixed the questions, right? Is the color is green? So this question is we are fixed. Why? Because in your attribute we are having a different colors. If suppose in your data set, if all the metric is actually, that means all the class having the same value, means we are ignored that particular feature because that is not a potential features. If the feature having a high variance, that capable to split, right? That feature alone, it's having a capability to split, right? So look at here. Once if we are executing this condition, it's splitted like this: green 3 mango and yellow 3 lemon, yellow 3 mango. So next condition is I am going to execute, and then next. So at finally we are builded the exact results, right? I hope so. You people are understand the general working of decision tree. Okay, from this example. Right now, what we are going to do now, we are going to investigate the terminologies of the decision tree. What are all the terminologies are there? So this is the actual the terminologies which is presented in your decision tree. Before going to investigate or build the decision tree, we have to understand what are all the terminologies which is presented, what is the exact role of that particular things. Okay, so in that decision tree, we are having a the first terminologies we have to concern the root node. What is a root node? It represents the entire population or a sample, and further gets divided into two or more homogeneous sets. Until to get the homogeneous set, we have to build the tree, right? Yes. So the root node, so which attribute is capable enough to act as a root node, we have to identify. Okay, that is the first terminologies we have to understand about the decision tree. Next we have to understand about the decision tree is your leaf node. What is a leaf node? So leaf node is actually the node we can't be further segregate into the further node. That is, we can say that is a, we can also call it as a decision node, right? That node only gives the decision. And also we can say in that particular node we are not having any mix up values. We are not having any mix up class values, right? That is actually we says it is a leaf node. Okay, the another one more thing is splitting. What is exactly the splitting? Splitting is nothing but it's just dividing the root node into a subnodes, dividing the root node or subnodes. Okay, subnode which is presented in the decision tree into different parts of the basis of some conditions. We are set to some conditions, and based on that we are trying to split the previous example. I hope so you just recollect the information about the previous example, then you easily map this particular terminologies with that particular examples, right? So next we have to understand what is a branch or subtree. So branch or subtree is actually formed by splitting the tree node, the splitting the tree or node. That is, we called it as a branch or subtree, right? If you are having a node, if you are further we are splitting, right, that is actually forms the branches or subtrees. It may be act as a subtree. We don't know whether it is going to give a leaf node or whether it's going to give a another parent node, right? Yeah, that is actually the branch and subtree. The another important thing you have to understand the parent node and child node. So root node is actually a call, we says it is a parent node, right? And all other nodes are actually branch, all other nodes are branched from its known as child node, that is from the root node. Okay, maybe you have a subtree. In that subtree, the one of the leaf node is going to act as a parent node. Am I right? While we are building the model in the previous example, once again I says, so in this particular thing, this is actually a child node for this root node, right? But this is going to be a parent node for this leaf node, right? Yeah, we'll see. I hope so you understand what are all the terminologies which is presented in the decision tree. Yeah, one more important thing is pruning. So pruning concept is actually opposite of splitting, right? So this is actually, if you look at the particular decision tree structure, if we are splitting further, what's happened, the complexity of the model gets increases, right? So what we have to do, we have to prune the some unwanted branches. So simply like how the farmer cutting the unwanted branches, right? So the similar way we have to cut the unwanted branches in the decision tree. So that is, we called it as a pruning. So now we are going to see the classifier and regression tree. Okay, this is the algorithm we are going to investigate. So first visualize the decision tree. So which question to ask and when? This is the actual scenario, right? This is actually the first visualization. So we have to understood which is going to act as a root node and which one is going to, which condition is we have to fix for that further splitting. Okay. So one thing we have to investigate, that question is actually when to ask and which one is we have to ask. So look at this particular scenario. The same example what we are discussed on our yesterday. That same data set is here. I am trying to explain once again by using a decision tree, right? So this is the whole decision tree for the application, the Outlook uh, outlook, that means the player is whether they are going to play or not based on the conditions. Okay, the we are investigated with the four features, right? Outlook, temperature, and then wind, humidity, right? So this is a exact picture, the picture of decision tree. First we are gets the outlook information, then we are splitted in the splitted further, right? And then here it is a, once again we are check the humidity, and then we are once again here we are checked the wind, wind condition, right? So and then finally we takes a decision whether the player is going to play or not. We will see how we are, that means the anatomy of this decision tree we will see in the upcoming slides, how they are building this, how they are fixing the proper attributes at the nodes. Okay, so so in this data set, I hope so yesterday itself I explained about this data set, whether the player is going to play or not. So I am not going to spend much time on the data set. So here we are having a 4 attributes and 1 target. What is our target? Whether the player is going to play or not based on the weather conditions, and based on the conditions is given here, right? Outlook, temperature, humidity, and wind, right? So out of 4, first, what is the first question? What is our first criteria in the decision tree? We have to know which attribute is going to play a root node role, right? So we are having a 4 options. So which is actually a best? I don't know, I have to investigate. Okay, so we just go here. So determine the attribute that best classifies the training data. That is actually your answer for this question so far. But we don't know how to we choose the best attribute, or how does a tree decides where to split, right? So that is we have to investigate once again. So far it's all we have to understand, right? So I'm going to answer for all this question in the upcoming slides. We will see. So this is actually the approach how the algorithms works. Okay, so first I try to take the Gini index. So this Gini index actually, it sorry, I'm going to take the information gain. Okay, this is a it's a clockwise direction. The investigation is actually, so information gain, it takes the information gain is the decreases in entropy after a data set is split on the basis of attributes. Why we are taking an information gain? Based on the gain, how far you are gain the information from the attribute, that is you have to investigate it by using an information gain. Based on that you have to fix the attribute, right, as a root node, right? Out of 4 attributes, which one is having a highest gain? That is we have to investigate. Based on that we are going to fix the root node, right? Then Gini index, it's actually measure the impurities. So where we have to once again split, that is we have to know. Okay, this is especially used in the CART algorithm, right? So CART is nothing but classification and regression tree. Okay, it does both the operations, right? It classifies as well as it also perform the regression operation also. That means it gives the continuous prediction value also, right? Then the next one is actually the reduction in variance. So what is a reduction in variance? Actually, it's a reduction in a variance algorithm is used for continuous target variables. This is especially for the regression applications. Okay, and this chi-square, it is an algorithm to find out whether the statistical significance between the difference, that means significance between the difference between the subnodes. So which is actually a significant subnodes and parent nodes. Okay, so this is how your CART algorithm is designed, right? So we will see one by one. So don't worry about all this metrics. We are going to see the practical manual solving of the problem, how we are manually build the decision tree for our problems, right? Then we are going to investigate how to implement this decision tree. So first, before going to know all those things, we have to understand the sum of the metrics. Guys, I try to map one more point. So in the last session, I investigated, that means last session we are discussed much about the mathematics, right? The fourth leg is we are actually skipped in the yesterday session. I hope so, whether if you people are noted, actually I purposefully skipped that one because that is one as a statistics, right? So that statistics is actually plays a major role here, especially in the decision tree algorithms. What are all the metrics we are using here? It's all comes under the statistics, right? We will see one by one. So first we have to know what is a entropy. Let us first understand. So before going to understand the entropy, because entropy is a impurity measure metric, that is actually the definition of entropy, but we don't know what is actually a impurity or impurity about the data, right? Consider this images. Okay, so I am illustrated here. We are having a one basket and one bowl, right? In the basket, it has a collection of fruits. Okay, in the basket we are only having a apple, and in the bowl we are having a label of the particular fruit. All the label are actually similar, homogeneous sets. It's an apple. Okay, so I'm trying to pick one fruit from the basket. Obviously it is randomly I'm going to pick fruit. I'm going to pick a label, right? Obviously both are getting matched, right? Because only we are having an apple, only we are having a the label is apple, label is also apple. Okay, so there is a no mix up data. So here impurity is zero, we can say. This is, we call it as a pure data, right? So what is the impurity? So consider the same scenario. Here we are having a basket with the 4 different fruits. Okay, okay, here we are having a bowl with the different class of labels, different class of labels. So randomly once again I am going to pick. So here I may pick the banana. Here I may got a cherry also, right? Because it is a random event, it may happen, you may get a cherry also. Okay, so in this scenario we can say the impurity is actually not equal to 0, because it's a highly impure data. Okay, because here also we are having a mix up, here also we are having a mix up. So what exactly the entropy says? So definition, it defines the randomness in the data. That is actually the entropy measures. That is because we are simply defined, it is a measure of impurity, right? So entropy is just a metric which measures the impurities, right? The first step is to solve this problem of the decision tree. We need this impurity. Where to we have to start? Am I right? If the data is not having an impurity, we can't build any decision tree. That is, we have to know. Whenever we are getting a data set, we have to investigate with the entropy. If the data set is having a only homogeneous data, we can't build a decision tree, right? That's why initially we have to measure a entropy. Look at here. So which data is actually possible to classify properly? A data which having a high entropy, right? So this data is only we are going to pick. So look at here. So before going to understand, so we are understood what is impurity, what is purity. Then we have to investigate what is the nature of the entropy. What about the function of the entropy? This graph investigate or illustrated the function of entropy. So look at here, the function of entropy under the 0. Okay, under the class 0th class, it is actually providing a very less value. If the data, all the data is comes under a 1, that is also providing a less value. So when the entropy gives a higher value, whenever I am getting a probability is 0.5. So if it is a 0.5, either it may comes under a class 0, either it may comes under a class 1. Am I right? Yeah. Under this situation only, your entropy gives a maximum value. Okay, this is the mathematical definition, the equation of the entropy, where entropy is equal to minus probability of yes log base 2 of probability of yes minus probability of no log base 2 of probability of no. Okay, so this is actually the class. The 0 and 1 indicates the class. This x-axis, it shows the probability of the particular class. That means either it comes under a class 0 or it is comes under a class 1. We all know about this. Am I right? If the probability is a 0.1 or 0.3, obviously it comes under a class. We are takes a decision. This particular data is comes under a class 0. Actually, this kind of decision only we are taking in the case of logistic regression. Logistic regression only produce the probability value. Based on that probability value only, we are classifies either the data is comes under a class 0 or class 1, right? That is what I am trying to say here. Sometime we may get a probability is 0.5, difficult to take a decision, right? So just I am trying to interpret with the value. Okay, interpret with the calculated value, where s is the total number of sample space, where P of S is the probability of yes. If the number of yes is equal to number of no, what happened? The probability of yes is given it as 0.5. Am I right? So entropy is 1. It's a maximum. Okay. So if it contains all the yes or all the no, the probability of yes is either 1 or 0. Okay. So under this case, your entropy tells it's 0. I hope so you people are understood. So next one is actually showing how this is actually showing the calculation of the entropy. If suppose I replaced my value, probability value is 0.5, which means your total sample should contain both the class. Okay, it contains both the class, that both the chances, actually this is, we can say, is because it is a probability, is both the chance. Okay, so probably 0.5 into log base 2 of 0.5 minus 0.5 into log base 2 of 0.5, right? It gives the entropy is 1. The similar way, if we calculate the value is actually 1, what happened? It gives the 0. So the probability is 0 is also problem, probability of 1 is also problem. You should have a 0.5. That means you should have a impure data. You have to mix it data. So we need initially to build any decision tree for your problem, right? So next one is, so what is the first criteria in your algorithm? Information gain. Okay, so the information gain, we need a entropy. That's why we are investigated about the entropy. What is the information gain? It measures the reduction in entropy. How far we are reducing the variance. Entropy measures the initial variance condition of your data, your whole data set, right? What is our ultimate? We are trying to reduce the variance. Am I right? That is what we are doing, right? Each and every leaf node where we are stopped, actually whenever we are get the unmixed up data, at that time we are stopped. So which indicates that we are trying to reducing the variance in each and every steps, right? So far it measures the information gain. It measures the reduction in entropy in the total variance, how far we are reducing, and then it decides which attribute should be selected as a decision node. This is very main. This is a very important step in the decision tree. This information gain parameter only decides which attribute is going to play the role of root node. Okay, because all your decision tree operations, it depends on your root node. If the sample S is our total collection, so how to measure the information gain? The total entropy, this is a total impurity of your original data minus the weighted average into entropy of each attributes. Okay, so don't worry guys, we will investigate with the problem how to solve this particular equation. So right now we have to understand what is the mathematical expression for a gain value. So total gain is equal to my total the entropy of total population of the data. Okay, this entropy of S is nothing but total population of the data, right? It's subtracted from the branch values, how far we are gained the information. Okay, let us build our decision tree. So now I am going to build the decision tree for this particular data, right? For the out of 14 instances, we are having a 9 yes and 5 no. Okay, in our data set. Okay, so here I am going to measure a randomness about this particular data, whether it has a uh, that means whether this particular data has a impurity or not, right? So first we need a entropy of whole population. This is my whole population. Okay, 14 samples with 4 attributes. The last column is tells about the target. Okay, so 14 samples with the 4 attribute, we can say it is a 4 into 4, sorry, 14 into 4 data. Okay, so what is the entropy measure says? Minus probability of yes log base 2 into probability of yes minus probability of no log base 2 probability of no, because here we are having only 2 class. That's why we are considering yes and no, because in the target we are having only 2 class. Okay, let us see. So what is the minus probability of yes into log base 2? Here probability of yes is we need, right? So how many yes is present in the data we have to investigate, divided by total number of samples. So 9 divided by 14 is multiplied with your logarithmic value. Once again here also 9 divided by 14, and here is actually 5 by 14. What is 5? So how many no is present in the samples? So 5 divided by the total samples is 14. Okay, so likewise we have to calculate the entropy. So 0.94. So totally this data having a 0.94 times of variance, right? So we can build the decision tree. From this value we understood that okay, it is possible to possibility to we can generate a decision tree for this particular problem, right? Next, what we have to do? Okay, what is our next step? We have to select the root node. That is our first criteria, right? So how to select a root node? We are having a 4 different attributes in my data set. How to pick my root nodes? Let us see. First, initially, we have to randomly select the root node, guys. We have to investigate each and every attributes. Then only we can select the root node in your decision tree, right? First, I am considering Outlook is going to act as a root node. Okay, so in the Outlook, what are all the possibility classes are there? Sunny, overcast, rainy. So out of sunny, what are all the possible target results? 2 yeses, 3 no. Next, overcast, all the thing is yes. So it is a homogeneous data. We can't split this particular overcast again. If it is a overcast, directly we takes a decision, they will play. Am I right? No further decision is required here. Okay. So next decision, what is the next possibility? Here it is a rainy. Okay. Under the rainy, we have a 3 class, 3 yes and 2 no. So here we have a chance to split. Here we have a chance to split, right? So we will see whether this Outlook is going to play a root node role or not. We will see that. So how to we select the how to take a decision actually based on your gain value, right? We are going to calculate a gain, which attributes having a highest gain, that attribute is we are going to fix as a root node. That is our ultimate, right? First, what we have to do, we have to calculate the entropy value. Okay, entropy value for this particular data, for this particular sunny. Okay, so especially this is not a entire data, guys. This entropy is not for entire data. This entropy is only for the first attribute. Okay, under the first attribute, especially for sunny. Okay, so entropy of Outlook is equal to sunny. So we already know what is the entropy formula. Minus p into sorry minus p of s. S means your class. P of s into log base 2 of p of s minus p of no into log base 2 of no. Am I right? So under this thing, what is the how many s is present? 2 s is present out of 5 data. So 2 divided by 5 log base 2 of 2 by 5. The same way you have to look at for no class also. So your entropy value of the Outlook at given sunny condition, it is 0.971. Similar way, you have to calculate it for overcast, and then you have to calculate for rainy. Actually, it is a typo mistake, guys. It is actually rainy, but answer is similar because the rainy and sunny, the answer is similar. Actually, 3 yes, 2 no. Here also 2 yes, 1, 2 yes and 3 no. Any of the count is similar. That's why we are getting a same answer. Okay. Here that's a typo error. It's actually raining. Okay. So once if you are calculated a entropy, next what you have to do, we have to investigate about the gain. How fairly we are gained the information from the Outlook. Okay. So far what we are going to do now, we have to calculate the weight average is multiplied with my entropy of the particular features. Okay, entropy of the particular features. That is what we are investigated in the formula, right, in the previous slide. So what is your weighted average is nothing but how many sunny is present in your total instances. So totally how many sunny is presented? 5 sunny is presented. Okay, so 5 divided by 14 is your weight average. Okay, this is how you have to measure a weight average. So 5 by 14 is for my sunny is into entropy of sunny is 0.971 is multiplied here. Likewise, you have to add for all the 3 classes because under the Outlook we are having a 3 classes. So for the total information is actually about the addition of these 3 classes. Am I right? Yeah. So this is a inter classes, we can say. Under the Outlook we are having a 3 difference. So we are added all the informations for the total information. For understanding about the total information, I have to add all the information. Okay, so it gives the value 0.693. What is our ultimate? Our ultimate is we have to calculate the gain. The information is not our ultimate. Our ultimate is we have how much we are gained from the attribute. Look at here. What is actually your gained from the outlook? The total sample entropy subtracted by outlook. What is actually I said? What is actual decision tree is doing? Takes the mixed data, trying to form the homogeneous data. That is actually the role of decision tree, right? So what here I am going to do, I am going to subtract my information from the total entropy. Okay, so that is my gain, how much I am gained from the outlook. Okay, so gain is equal to my total entropy. In the first step we are calculated this one, I hope so, minus my information. What is just now we are calculated the information. This just a minute, I want to once again show the formula, then it is easy for you to calculate. So this is the information minus this is a weighted average, what we are said right now, into entropy of the each features. Okay, okay, I hope so it is easy for you to recollect all those things. Yes, so this is where we are actually, yeah. So here I try to calculate the gain of outlook is 0.247. Similar way you have to calculate it for rest of the features, right? So what is the rest of the features? Temperature, humidity, windy. So for wind, we have to once again split it as, because in the wind, how many classes are there? False and true. Is it two classes? And under humidity, once again, you have two classes, high and normal. In the temperature, we have two classes, three, hot, mild, cool. Okay. So the similar steps, what are all the steps we are discussed for our outlook? We have to do all the steps. So we have to calculate a entropy for yes. We have to calculate, true. We have to calculate a entropy for true. We have to calculate a entropy for false. Once again, you have to calculate the information from the wind. What is the information from the wind? And then you have to calculate a gain value of the wind. I hope so you understand here. This is also the typo error, guys. This is actually the information from wind. Okay. Okay. So many typo error. It's actually wind. So likewise, similar way, you have to calculate for temperature and wind. Sorry, humidity. So this is my total result. Okay. So first, initially, I can say my total information about the outlook. That the total information about the outlook is 0.69. The gain is 0.247. Whereas for temperature, the information is 0.91 and the gain is 0.029. Similar way, humidity and wind. So which one is having a more gain value? Which attribute gains a more information? Your outlook is gains a more information. So we are understand out of the all the attributes, outlook is having a better option to fix as a root node, right? So far outlook is our root node. So next, okay, the root node is we are fixed. So under the root node, we know we are having a three classes. So we are splitted sunny, overcast, rainy. Okay. So next, where we have once again, which question is we have to fix, and which node is we have to fix. Once again, the question comes, right? So for that, you have to investigate where we are having a homogeneous set, where we are having a non-homogeneous set. Anyhow, under the sunny, we are having a homogeneous set. We already know that in the initial stage itself I shown. In this case also we are having a non-homogeneous set. But in the overcast, we are having a only homogeneous set is called yes. The target value is yes. So outlook is actually overcast. We takes a decision. Yes, the player is going to play. Okay, the further in the further splitting is not possible, because all the yeah, data is actually comes under one class. If you measure a entropy, what happened here? Obviously zero, right? Because it is it is a pure data. We can't once again split this data, right? So we are stopped here, and this is going to act as my leaf node. This is going to act as my leaf node. Okay, next we are going to investigate here. If it is a sunny, we are having a, if even though if it is a sunny, we are having a 3 yes, 2 no's. It's a non-homogeneous data. If it is a rain, here also we are having a 2 yes and 3 no. Here also we are having a non-homogeneous data. So what we have to do, once again we fix the attribute node here, and then we have to fix the question, further split the particular data up to the pure data, up to attain the pure data, right? So you need to recalculate the things. So this is how the complete tree looks like, guys. So I will tell how we are fixing these things and all. Okay, this is how the complete tree. Once if it is a outlook, then it is a sunny means, once again we can't take a decision because it is a mix up data. Once again you have to investigate humidity also. If it is a sunny, you have to investigate humidity. If humidity is high, their player is not going to play, it is no. If it is a humidity is normal, the player is going to play yes. Similar way, if it is a wind, we have to investigate, sorry, if it is a rainy, it just once again we are split, we are fixed the node, because the rainy is also having a mix up data. So here once again we fix the node to once again we are drill it up to get the homogeneous data. So here we are fixed the windy, and we tried if it is a windy, if it is a strong, we takes a decision no. If it is a weak, I'm going to take a decision yes. Okay, this is where this is my complete tree. So how we are fixing this humidity and wind? Any idea? Any idea? Any idea? Yeah, probability is yeah, exactly. The question is actually from Dr. Murthy. Yes, exactly. The minus log of the 1 by probability is actually I wrote it as a minus log. Exactly. Yeah, why are taking a negative? Yeah, exactly. This is actually the information formula. If you look at the information formula, it looks like pk into log of 1 by pk. So I changed my 1 by pk as pk. That's why I am actually included the negative signs. So I just try to answer your questions. That's why I am seeing here.
Suresh?
Yeah, yes, sir.
Yeah, it's a time at 11.
Yeah. That's why I stopped, sir. I am seeing the chat box.
Okay. No
Answering
problem,
the questions.
no
I'm
problem.
seeing the chat
So
box.
that we can take a break and we can come back by 11:30 and
Yeah,
we
yes,
can
sir.
take it up again.
Yes, sir.
We can continue.
Yeah,
Okay.
yes, sir.
Just.
Yeah. Thank you, participant.